In this video, we're going to cover stationary points. We're going to start with the very basics, that being derivative equals 0, and then from there we'll see how we can apply that to the more complicated questions, like your exam-style extended response questions. Enjoy! Alrighty, let's make a start. So this lesson will finish up pretty much all of the remaining applications of the derivative, starting with finding stationary points. So as far as what stationary points are, you've actually seen all of them so far. They are local maxima, local minima, and stationary points of inflection. So maxima, obviously, you're looking at a maximum point on a graph, the tallest y value there. Whereas for minima, it's the opposite, it's the lowest y value. And then lastly, you've got your stationary points of inflection, which came from the cubics when you would have first seen them. A little quick note on those points of inflection. I do really specify or stress that this is a stationary point of inflection. There are other kinds of points of inflection that aren't necessarily stationary points of inflection. What characterizes a stationary point of inflection is that it has a gradient of 0 at that spot, whereas other points of inflection aren't necessarily going to have that. Points of inflection are basically just sort of like these little wiggle spots in a graph, and you see a whole bunch of them when you sketch any circular function type graph. So at these spots, these are not gradient 0. At these spots, the gradient is 0. That's just a minor thing to keep in mind there. But okay, so what does calculus actually allow us to do here? Well, we can find all those stationary points because every stationary point is going to have a gradient of 0. And so if the derivative is all about finding gradients, then all we have to do is find the derivative and set it equal to 0, because we want to find all the spots on the graph where the gradient is 0. So with that in mind, we find derivative, set it equal to 0, solve for x, and then if you want the full coordinate, you're just going to sub that x that you've solved back into the original function, not derivative, but the original function. Reason why? The original function has x and y values, the derivative function has x and gradient values. So if you want to coordinate x and y, you want to be back in the original function, not the derivative. But okay, here's an example. Find the stationary points of this cubic. First thing we're going to do is find our derivative, f dash of x. So f dash of x is therefore 3x squared minus 12, and then we're just going to set that equal to 0 for that second stage. This one is a quadratic, and so it ends up having two solutions. You're going to have plus and minus 2 for this one. So that implies that this cubic is going to have two stationary points, which you should be at least familiar with based on how to sketch a cubic like this. So we've got two x coordinates to work with, but we want to have the full coordinate at that spot. So we're going to sub both of these into f of x to obtain the y values. So starting with x is positive 2, you sub it into f of x, that's going to give you y equals negative 16. If you were to do the negative 2 variant, you would get the positive 16. So if you remember from when you were sketching cubics before, the best you could really do was grab your x-intercepts and then get the overall curve looking right. Now that we have derivatives, we can actually find these stationary points with the derivative. So it's now possible to achieve those key features. If there's any questions about that, let me know. Otherwise, I'll move on. Okay, so one other application of knowing how to solve stationary points is that it gives you another way of creating an equation for solving unknowns. So in this case, we have a families of functions style thing where we've got this unknown a in here, as well as the x and y. But we are told that there's a stationary point at x equals 3 in this situation. So typically, when we have information about a point, we would sub it directly into the function. We would have an x and a y, leaving a on its own. However, this one only has the x coordinate. So using the strategy we've been accustomed to isn't quite going to work, at least in this case. However, something very similar will be used in this case. The fact that it's a stationary point matters a lot. We don't know the y value at that spot just yet, but the fact that it's a stationary point means the gradient's going to be 0. So anytime you're told information about a stationary point, the equation that you can always create from that is f dash of x is equal to 0. So we get our f dash of x by finding the derivative of f, and then we sub in our x equals 3 into that spot, and we know the gradient should be 0, hence we're going to equate our derivative to be 0 at x equals 3. So we plug in 3 into all the x's here, equate it to 0. From there, rearranging for a isn't quite so bad. If there's anything to clarify there, feel free to let me know. Otherwise, I shall move on. This is going to take that to the next level. So if there's any clarification, definitely ask now. But okay, so this one here. Find the x coordinates. Oh, I saw you come off mute. Was that a question or?
Oh yeah, I was gonna ask, could we just go over that last question again? I kind of lost you after we subbed in the derivative.
Subbed in the x equals 3 into the derivative?
Yeah.
Yeah, so are we fair enough as to why we're subbing in the x equals 3, or do you want to explain that as well?
That's because it's a stationary point that was given to us.
Yeah, correct. So x equals 3 is going into our derivative function because that is, yeah, the x coordinate of a stationary point. Are you also okay with y that equals 0?
I'm not sure, but is that because the gradient at a stationary point is 0?
Correct, yeah. F dash of x is all about gradients. So if I want to find gradient 0, I'm going to replace that f dash x symbol with 0. So what that is effectively as if I had known x and y, right? I'd plug in my y, I plug in my x, I solve for a. In this case, I know f dash and x. F dash is 0 because of the gradient being 0. X is 3. If you put a 0 here and a 3 there, it's just rearranging for a at that point. Is that fair enough now?
Yeah, thank you.
Sweet. Okay, cool. Now, here's similar concept, but we're going to ramp it up. So we still have a families of functions style thing, but now n is in the power. And as far as what we do here, nothing's actually being done differently. It's just that there's a lot more terms to now deal with because, well, simplifying this sort of stuff when there's an unknown in there makes it a bit more challenging, or at least a lot more to keep track of. In fact, that's why they only ask for the x coordinates here, because subbing everything back in afterwards, bit of a nightmare. And so this one they like to simplify. And I pulled this from one of the textbook things. But anyway, cool. So we want to find x coordinates of stationary points. So just by seeing that statement there, you could ignore everything else that you're seeing in the question, and immediately the first thing you should think of is, I need to find derivative and set it equal to 0, because that's how you always solve the x coordinates for your stationary points. So never mind the fact that this is a nasty function, we're still going to have to deal with f dash and then set it equal to 0. But okay, so we're following that procedure. First thing is going to be, how do we actually find the derivative of this function? There's a couple of things to worry about. The first is that it's a product of two things, and so the product rule is going to be required here. Pre-product rule, pre-learning of the product rule, we could usually expand this out. The problem with expanding this one out now is that you've got a power of n in there. And so because n has no known upper bound, right, it's just some natural number, expanding that out becomes impractical. Just can't really be done. And so we're going to have to rely on our product rule knowledge, which is you define the first two functions that are multiplied together. So it's going to be this 2x minus 1 to the power of n is going to be our u. And then this second part here, the x plus 2, that's going to be our v. From there, product rule says we should derive both of those functions. So n is going to come out the front and it's going to be reduced by 1. And there's also a bit of a chain rule aspect here. So you're going to have to find the derivative of the inner, which is 2. That's where this 2n came from here. This whole thing as a whole does appear on your formula sheet. Does anyone need me to break it down beyond this one-liner derivative? Let me know either by hopping off mute or in the chat. But anyway, it'll also be the derivative of v. That's pretty quick. X always just goes to 1, constants disappear. Oh, here we go. Yes, please. Sure. Let's give it a shot. So the lengthier chain rule version of what's going on is we have our function. It was u equals 2x minus 1 power of n. So this is closest to a power function, right? It's something raised to a power. And so one of the things we're going to have to worry about here is that this, because there's something other than just x in that spot, we're going to have to do a substitution. Now, just for simplicity, I'm going to rename this as y, so I can label the inside as u. U is going to be 2x minus 1, and therefore our new function y of u is going to be u to the power of n. I will take a quick pause here. I just noticed a new student has joined. Dane, I do have a couple of different cameras around here. I've got a camera for a screen share, and I've got a camera for some handwritten notes. Let me know if there's any issues getting to seeing those cameras, and I'll try to sort that out. But okay, back to the solution. So, chain rule, we've split up our inner function and the outer function, rewritten purely in terms of our substitution. From here, chain rule says find the derivative of each of these. So u dash is going to be 2, and then y dash of u, well, n comes out the front, and then the power gets, and the power gets reduced by 1. So n times u to the power of n minus 1. Bit weirder because you got some letters there, but that is just the basic derivative of your power function. Now, from there, chain rule says multiply these two things together. So the derivative of this term that we started with, y dash, is therefore going to be 2 times n times u to the power of n minus 1. Now that's great and all, but we don't want to have a u in here anymore. We do want this purely in terms of x where possible. In this case, we do have that other n to consider as well. So all we're going to do is replace that u with what it is, which is the 2x minus 1. 2n bracket 2x minus 1, all to the power of n minus 1, and that's what we had on the main screen share with the pre-written notes. That is the full chain rule bit there. Is that all fair enough how that came about now?
Yeah, that's clear, thanks.
Sweet. So what I will do also is pull up a formula sheet just so you can see for that particular question, you don't really need to go full chain rule there because the formula sheet that you'll get actually has a pre-solved version of that. So if you take a look at this section on the formula sheet here, this is where you have some linear raised to some power. So it's actually quite similar to what we've got. The only difference is that we've written a is 2 and b is -1. You can see how that coefficient of a ends up out the front. The power then goes down and gets reduced by 1. So you can refer to this spot on the formula sheet if you like, or practice a few more chain rules. Either or is fine. But okay, that's where this came from. As a quick reminder, we got here from doing product rule on this function because we're trying to find its derivative. So we have everything we need for product rule. We're going to do our cross multiplication, which is just this multiplied by that plus this multiplied by that. Or, vu dash plus u v dash. Again, this is a thing on your formula sheet. It might not say dashes, but you should be aware of the different notations for derivatives. So we just plug in all the terms in the correct spots and you're going to get a nasty looking formula like that. That is our derivative. If you want, you could start expanding things. It's probably better off you leave it for now because the next step of this, because we're trying to find for stationary points, is we're going to set our derivative equal to 0. That's blanket statement what we always do. Now, this you need to be able to identify is a kind of polynomial. The fact that n is is a natural number means that for any value of n, this will always look like some polynomial. It could be power of 10, it could be power of 15. It's still got to be a polynomial. And so the reason why that matters is because the way we solve polynomials informs how we would solve this, which would be a sort of null factor law / factorization approach. Currently, we don't have it in that situation, right? We've got a plus that's separating these two terms. However, we can notice is a common term between the two. It's not fully common, right? This one's power n, this one's power of n minus 1. But because the bases are the same, it's like having an x cubed and an x squared. You can take out a common factor of x squared and just leave one of those left behind. So as far as that works, this being n minus 1 means that this is the lower form, and so you take that whole thing out the front and you just leave one copy of this behind. Is it fair enough getting from here to here? That can be a bit complicated to see. I've tried to highlight it in a way. If that's not clear, let me know. But point being, if you have that, actually another way to think about this would be grouping, right? So if that's clear, consider it grouping. You could even replace this 2x minus 1 with a dummy variable, a u, and then that way it becomes a bit clearer how you might replace that. But okay, the whole point there was to get a null factor law, and sure enough, that's what we've achieved. We've got this multiplied by this equals 0, which means either this or this equals 0. So you take each stage, equate them to 0. Nothing too crazy going on here. Doesn't matter what this power is, you would always just take the root of that. So if this was a power of 4, you would take the 4th root. If it was a power of 5, take the 5th root. That works no matter what this is, and so you can always just cancel that directly out and get your x equals a half. And then from here, well, this is just linear. Nothing too crazy going on here. You're just rearranging for x, collecting some like terms, and that's going to give you your two x coordinates of stationary points. So this one, bit of a monster question. Just wanted to show you that it doesn't really matter how complicated the question gets, you're still following largely the same steps. In this case, we didn't go all the way to finding the full coordinate because, well, sure, subbing in x equals a half into this wouldn't have been that bad, but this, that's another story. So ideally well, the book didn't want you to do that, and so I wasn't going to take it that far. Cool, so that's all about finding stationary points. Up until this point, we've been able to find stationary points, but one of the issues we have there is it doesn't actually tell us what type of stationary point we have. We don't know if it's a minimum, we don't know if it's a maximum, or if it's an inflection point. That's where, okay, there's a couple ways you could do this. My recommended way is the so-called double derivative test. It doesn't appear in the book. God only knows why. Basically, what we're doing here is we're taking it a step further by finding the derivative of the derivative. So we had a derivative of x squared minus 3x in this case. The double derivative would therefore be 2x minus 3. Finding the derivative of this, dash dash. The reason why I teach this particular method is because finding derivatives for polynomials, pretty chill. As far as identifying how to use that to figure out what type of stationary point you have, it's basically the same as how you would treat the discriminant of a quadratic, where you're going to have a less than 0, a greater than 0, or an equal 0 situation. If after you sub in your x coordinate, it becomes negative, you have a maximum. If it's positive, you have a minimum. If it's 0, you have an inflection point. So if your understanding of discriminant is chill enough as far as being able to identify between the three criteria, this should be a similar level of difficulty for you. As far as the overall steps we're following, it'll be these. We'll look at an actual example to put this into practice. But that's just the broad strokes of what we're doing. Okay, so from here, find the nature of the stationary points of this cubic. This is a cubic we've seen before. I'm just going to borrow the actual stationary points from earlier so we don't have to double up that work. So that was these solutions from before. Now we're going to try and figure out which one's the maximum and which one's the minimum. And we're going to do it in a way where we don't have to draw the graph. So, find double derivative. We had f dash was 3x squared minus 12. Double dash is going to get it down to 6x now. From here, we take the x values from these stationary points and chuck them into our double derivative. So f dash dash of 2, f dash dash of minus 2. That's going to give us 12 and negative 12 respectively. All we're going to do now is analyze it. Did we get a positive? Did we get a negative? Did we get a 0? This case, we got a positive. Positive means greater than 0, which means that was, oh hang on, did I say that wrong? No, yeah, that was a local minimum. So positive is minimum. The next one was negative, negative 12. Therefore, we have achieved a local maximum at that spot. So that's all it ends up being. Find double derivative, sub it in, is it positive, negative, or 0? That's the extent of what you'd be doing for the double derivative test approach. And again, that's going to match up with what we had on our graph. Now, I teach that because it's fast and certainly easy, I would say, because it's the same level of difficulty as the learning discriminant there. What the book does is they want you to do these sign tables. In fact, I won't find a different example. I'll do this example as well. They want you to do these sign tables, which basically means you want to find where all your stationary points are. We'll do this on the handwritten bit now. So we had an x equals 2 and an x equals negative 2 for our stationary points. The way the sign tables work is that you pick some values that are left or right, or left and right rather, of each of those values, and you test the derivative at that spot. So you would start with the ones you do know, which is negative 2 and 2. Those are going to be represented by flat lines, which is a 0 gradient. What you would then do is you have your f dash of x is 3x squared minus 12. You test these 3 points and see if you get positive, negative, or 0. If you get 0, something's gone wrong because you should have found that earlier in the stage, in the simplification. But basically what they're saying is, okay, let's say we test our 0. So we're going to have f dash of 0. That's going to go to 0 minus 12 negative. So negative means you would draw a slope going downwards because, well, that's what a negative slope looks like. Then you would test 3 and negative 3. Because we're squaring it, those are both going to end up being the same thing. So f dash plus minus 3 is going to be 3 bracket plus minus 3 all squared minus 12. 3 3s are 9, and then 27. So 27 minus 12, that's a positive number, and so both of these should be pointing upwards. Are sign graphs only a requirement if the question says so, or is that what VCAR prefers? If the question says so, yeah, definitely do it. I don't think VCAR has a preference either way. I'd have to double check and see if a double derivative solution ever shows up, but it is valid. They don't, yeah. VCAR very rarely will force you to use a particular method for something. They will force you to write your answer in a particular form, not necessarily use a specific method for it. Yeah. I'd have to double check exactly if double derivative ever shows up. But it's kind of like, if you've seen some of the past exams, they'll have these situations where they'll say, hence or otherwise, solve a thing. That or otherwise is there because they want to make sure that you're, they're not shoehorning you into a particular way of doing things. But if it does say use sign graphs, then do what I'm doing here. Absolutely, yeah. But okay, so we got a positive result here, which would mean that both the 3 and the negative 3 should be a gradient pointing upwards like that. And then from there, all you're doing is you're looking at the shape. This looks like a maxima, this looks like a minima. So the negative 2 should be a maximum, the positive 2 should be a minimum. To me, that's a lot of subbing in for no real benefit. Double derivative and then testing the points you already have, I feel is easier. But feel free to use either method you like. I'm not fussed either way. Okay, those are the things you've got access to there. This next example here is a bit niche. I think I'll leave this one for either when we get to it in a question, or yeah, we'll leave that one for now. This gets pretty niche, so we'll leave that there. Okay, so all this talk about finding stationary points, why do we care? Well, beyond the fact that the book is telling you to find them, in the real world, they can be used to find maximums or minimums of a particular function. Could be an area function, could be a volume function, could be whatever that quantity ends up being. Typically, when you draw the graph of that particular quantity, you're going to have a turning point, and that's going to be the key feature that you'll be looking for. Previously, you would have seen a whole lot on quadratics, right? So if I draw a quick one up, pretty much every time you've done a quadratic, you'll have a sort of hump like this, and the whole point was to find this turning point always. You would restrict it from here to here. You want to find that. Now for quadratics, that's easy, right? You can just do your turning point form. You can do axis of symmetry. You've got a lot of options available to you for finding that turning point. But when it's a cubic, it's not quite so simple to find those stationary points. Until now, obviously. Now we can use derivative. So the typical thing for a cubic is like that. You'll have a full cubic for your particular circumstance. You'll cut out all of this because you typically don't want negative anything. The difference between this hump and this hump is that this one is usually slanted further to the right than this one is, and so you can't just go dead center to find it. You do have to use a derivative approach. But that's just some hypotheticals now. Let's look at a few other examples. So this one I pulled from a genuine exam on the screen share. This is one of the cases where you have a shape that is inscribed inside of a another shape, actually, or bound by a curve. So I remember we had, I think most people are here from that last group class, where I talked about how you'll have a generic point on a curve, and you want to get it into a scenario where you don't have a whole bunch of letters in there. You want to have just a single variable so you can actually plot that thing. So what's happening is we have this semicircle equation, and there's some random point x that exists somewhere along this domain, and from that you could create a triangle effectively, and we want to maximize the area of this triangle. If you want to maximize something, you first need an expression for that thing. So basic area of any triangle is going to be half base times height. So our goal is to figure out what's our base and what's our height, and we want to do it in a way where we only have one variable in it. Base is just this. So if it goes x in this direction and it goes -1 in this direction, then the net result is going to be x plus 1. That's your full base. As for this height, we can't just say y, even though the y coordinate is technically correct. We want to get it in terms of x purely. So because this is an intersection on the curve, instead of just saying y there, we know that this x here is the same x from here. So this y is the same y from here. Instead of saying y, we're going to say square root of 1 minus x squared. So that's our new height there. So instead of saying half base times height, we now have half that times that. Everything is purely in terms of x. We can now work with this. When trying to maximize, there's going to be some turning point here. And so we're going to start by finding derivative. If you have to do it by hand, you would do it, well, there'd be a double chain rule. No, just a single chain rule going on here and a product rule here. Won't get too much into the weeds of this. This would have been, well, no, it was a tech-free. Yeah. Yeah, okay, why not? So product rule, because it's a product of two things, x plus 1 and square root. And so that's this and that. Whoops. Then from there, product rule says we want to find the derivatives of each of these. There's a chain rule associated here. That's what all this is talking about. Damn, this one needs a overhaul. This is kind of nasty. Point being, find the derivative of both of these. That's going to give us u dash is there, and v dash is a half coming from that. I know this is kind of nasty. We'll just take these for granted, because usually this will be like a tech-free sort of situation. Sorry, usually a tech active. From there, product rule, so sub it into the right spots, a whole bunch of algebra, and we'll get something like this. The main thing to be watching out for here would be try to get it down to same denominator. The reason why is because when we set it equal to 0, because that's how you find your stationary points, you can always just multiply both sides by whatever that denominator is. So algebra aside, this isn't really an algebra class, it's more so the broad strokes on how you would do it. You set it equal to 0. From there, solving this isn't super tough, because you just got your numerator equals 0, it's just a quadratic. And so either use your factorization null factor law, or you could use quadratic formula to get those. All in all, we figured out our x coordinates for which the gradient is, which the derivative is equal to 0. There's two of them. How do we handle this? Well, we go back to the scenario that we had. We figured out it was either x equals a half, which would be roughly there, or x equals -1, which would put our x coordinate right there. So if you think about which one of those is likely to maximize the area of the triangle, we're basically saying, would I rather put my coordinate b here, in which case the triangle would look something like this part of it, or would I rather put my coordinate of b here, in which case there is no triangle. So using a bit of logic, you could then say the x equals a half is the only one that's worth doing. If you wanted to prove that in a different way, you could do the double derivative test and then prove it's a maximum at that spot. But I mean, let's not do the double derivative here. That's a bit nasty. And then yeah, that'll give you the x coordinate for which there's a maximum. If you need the actual maximum, you plug it back into your area formula. Now, I know there's a whole lot of like math to be done here, but broadly speaking, it's the exact same steps you're already used to with the quadratic, which is draw the quadratic, find the turning point, sub the x value into the equation to get the y value at that spot. That is the maximum that you're looking for. Oh, I did have a tech active version of this. That would have been nice. So tech active, obviously, you can see it's a great deal simpler, because you can use functions like fmax on your cas that'll just tell you where the maximum is, rather than having to do derivative equals 0 and solving. But these are all going to be there in the resources. Cool. All right, so that's where it's headed. We may or may not actually do any questions on that just yet. I think for now, we'll focus on just making sure we understand how to find the stationary points, full stop. So was there anything about that you wanted me to clarify in more detail, or shall we move on to some questions? I'll take a quick pause to drink while you have a think about that. All right, cool. So back to basics, actually finding stationary points. Every single time, derivative, well, I won't actually say anything there. 1a we already did. I pulled that one from the book to write my solution. So we'll look at part B here. So I'll go to the handwritten bit and I'll just write that out, and then we can work from there. Okay, g of x is equal to 2x squared minus 4x, and we want to find the stationary points of this function. So, how do we do that?
We first want to find the derivative of g of x.
Absolutely. G dash of x. What's the derivative?
Is it 4x minus 4?
4x minus 4. Absolutely. Power goes down the front, reduced by 1. Same thing with the minus 4x. All right, we got our derivative. Now what?
We want to solve for x.
Solve for x is correct, yeah. How do we...
And you equate it to 0, right? And you get x is equal to 1.
That's it. Yeah, absolutely. Equate
And
out
then
the derivative to 0.
I think we just sub it into the original function to get the y value.
Sure do, yeah. Because at this stage, we've figured out the x coordinate of our stationary point, but we want the full coordinate, which means subbing it back into original. 2 times 1 squared minus 4 times 1. 2 minus 4, going to have minus 2 there. So final coordinate, or final answer rather, would be 1 comma negative 2 for that. That's pretty much it really. So that's for power functions. Stationary points, it doesn't matter what function you're given. If you look back at the book, there's exponentials, there's logarithms, there's products. So product rule, quotient rule, chain rule, all these things apply. Yeah, that's really about it there. It's a bit more interesting in 3b, we'll say, because 3a I again pulled from the book. So I'll write out 3b. That one is h of x is equal to x cubed minus bx squared minus 9x plus 7. And stationary point at x equals 1. Cool. And our goal is to solve for b in that situation. What might we do?
Find h dash of x.
Yep, h dash is a great start. What's it going to be?
Is it 3x squared minus 2bx minus 9?
Yep, perfect. Yeah, so that any other letters than x you treat as constants. That's why it sort of just chills there. Like for example, if this had like a plus c in it and you wanted to do the derivative, that c would just flat out disappear because you treat it like a constant. Okay, let's get rid of that. Yeah, so we have our h dash. What are we doing from here now?
We know that if we sub in negative 1 into h dash of x, so if we do h dash of negative 1, it should be equal to 0 because it's a stationary point.
Yeah, correct.
And then that should allow us to find b.
Yes, it should, because you're going to replace all the x's with negative 1, which I realize I wrote down slightly wrong. It should have been negative 1. Yeah, negative 1 into all the x's, and then 0 into the h dash spot. So this, and then 0 here. So 0, 3, negative 1 squared, minus 2b bracket negative 1 minus 9. It's going to be 3 plus 2b minus 9. 9 minus 3 equals 2b. 6 over 2, so 3 equals b. Yeah, that's all. Nice. Everything else is going to be some form of complicated version of that. So if you look at like question 4, there's more unknowns, but there's also more things to create equations from. So we're told it passes through a point and it has a stationary point here. Actually, this one is worth having a think about. You've got 3 unknowns here, but you're only told 2 points. The theory of equations still says you would need at least 3 equations to solve 3 unknowns. Where are my 3 equations going to come from? Question 4 there.
Would one of the equations just be like the similar process to what we just did?
Yeah, correct. So you'd be using the stationary point, so you'd grab your derivative, sub in the x equals 1, that gives you one equation. Yep. 2 more left.
Would another equation be when you just sub in the given point?
Yep. So you're talking about this one?
Yep.
Yep. That's number 2. Number 3. 1 left. Bit sneaky.
This might be a shot in the dark, but is this something about the derivative?
Actually, so not about the derivative this time. We've used our derivative for the stationary point. Now, yeah, the cheeky bit here is that a stationary point is still a point. And so, yes, you've got the point x equals 1, derivative equals 0. That goes into derivative. But you've also still got the fact that x equals 1, y equals 3. And so, stationary points count for 2 when dealing with these situations. You've got the derivative version of it, and you've got the xy version of it. That's where the third one comes from. So in total, you have sub in x equals 0, y equals 3 here. That's going to give you, well, you can already see d is going to be 3 there, because x equals 0 kills all this. Then you have the derivative of this, x equals 1, y dash equals 0. And then you have just y equals 3, x equals 1. Those are the 3 equations. That is just simultaneous from then on. That would be revision for yourselves to do. I'm more so interested in showing you how you use calculus to start it out. Okay, next one up. Very similar circumstance, 3 unknowns. We want to have 3 equations. This should ring a bell pretty quickly, where the first 2 equations are going to come from. So I guess the main thing will be, what does this bit tell us? How's this part important for creating an equation?
Since the 2 lines are parallel, would you just want the x's to equate to each other?
The x's to equate to each other. How do you mean? What would that look like?
The value of x should be the same. So like
Value of, hang on, tangent is parallel. Well, parallel doesn't necessarily mean they both, they're touching at a point. So this would mean, if I were to draw this out, it would look like we have axis, we have y equals 4x, which would be quite a steep line like that. And then we're going to have some quadratic. Now, one way this could exist is the quadratic could be out here, and my tangent line could be like that. The only requirement is that tangent of this is parallel to that, which this diagram is supposed to demonstrate. That's what we're aiming for. That's what Sanjay said. you sub in x equals 2, which gives equation of y when x equals 2. If you sub in x equals 2, where are you saying to sub that in, Shanjay? Is that into this quadratic or the linear? Quadratic, yeah. So if you sub that in there, sub in x equals 2, you're going to have a y and a c in that case. That okay? That might work out. I think it probably pays to see what the actual, like, what these end up looking like. So basically, when you create these equations, in both cases, you're eliminating an x and a y, or an x and a y dash. So you're leaving only the a, b's, and c's in your equation. If you just sub in x equals 2 in here, you're also putting a y in there, which makes it, I don't want to say unsolvable, but I'm pretty sure it won't quite pan out too well. The key thing to watch out for here is this parallel bit. So the fact that at x equals 2, it should be parallel to y equals 4x. And now that I'm saying that out loud, my quadratic is clearly on the wrong side there. If I draw that quadratic in a better spot, like let's say here, for example, and this is x equals 2, then the only goal is to make sure that these are parallel. So basically it means target gradient at this spot needs to be 4, right? For this linear to be parallel to this linear, because that linear, that is y equals 4x. So basically I want to say that gradient at this spot on my quadratic should be 4, and that spot is x equals 2. So derivative being, which one was this again? It was question 5. So 2ax, where is it? 2ax plus b. So that would be the derivative of this generic quadratic that we have. Setting that equal to 4 and setting our x equal to 2 leaves us with just a's and b's, just like how we would have gotten with our stationary points. We now have 3 equations that have a, b's, and c's in them. From there, you would be able to do your simultaneous. So, keyword there being the parallel, keyword here being stationary points. Things to do with gradient become kind of important. Clear enough how we would create those equations, or should I go into more detail what each of those equations would have been? Into detail? Yeah, sure. So for exactly this one here, we'll finish off that parallel bit. So we have our derivative, which is 2ax plus b. We know the gradient must be 4, so 4 is our y dash. We know the x must be 2, so we're going to have 2a times 2 plus b. 4 equals 4a plus b. So that's one equation done, which will have both a and b in them. The next 2 equations are going to come from our stationary point. So we have a stationary point at 1, minus 3, which means, first things first, this is an x and y pair, and so we can take our original y equals ax squared plus bx plus c, replace every x with 1 and every y with negative 3. That's the first way you can use a stationary point, just like any other point. Negative 3 equals a times 1 squared plus b times 1 plus c. Negative 3 equals a plus b plus c. So that's another equation that just has a, b's, and c's in it. And then lastly, stationary points being a gradient of 0 means that if I subbed in x equals 1 into my derivative, this one up there, then it should equal 0 because gradient should be 0. So 0 gradient is equal to 2ax, where x is 1, and then there was the plus b that was at the end here. So that gives you 0 equals 2a plus b. That is the third equation that has A's, B's, and C's only in them. To further demonstrate what was wrong with just subbing in x equals 2 into the original function, here's what you get. Y equals a bracket 2 squared plus b bracket 2 plus c. That's going to give us y equals 4a plus 2b plus c. So you've got an additional y that's now in there as well, whereas all of these only had a, b's, and c's, which you can then, which you could solve in that case. But in this case, because you have a y in here, there's not much to be done. This just becomes simultaneous equations now. We could do a revision on that if you do need to revise how to do simultaneous here. But I think we'd be better off if we start looking at least 10D, which would be the types of stationary points. So if you do need to revise simultaneous, be sure to go back to chapter somewhere around question 2. So 2C and 2F. Yeah, 2C, 2F. There are more complicated questions in here, but as long as you get the gist of what's going on here, that should prepare you nicely enough for those. All right, types of stationary points. So here's a look at those sign tables. Feel free to use them if you like. Double derivative is my preferred way of doing it. A whole bunch of examples there. Okay. So what I'll do is I'll just grab a quick screenshot of how you can do. Yeah, I guess even this whole summary is nice, but the ones we'll specifically care about will be the second framework, which I'll put as a screenshot in the chat. So you can use either double derivative test, or you could use your sign graph, whichever one you'd rather do. We shall start by doing, what's a good one? Yeah, why not? We'll just start with A, nice and simple. So I'll just write that one down. F dash of x is equal to 4x squared. Cool. So the whole goal here is to figure out where the stationary points are, and then after that, figure out what type they are. Now, we've been given f dash right off the bat, so when it comes to finding stationary points, it's just gradient equals 0 again. 4x squared equals 0, x equals 0. So our stationary point, or at least the x-coordinate of it, is going to be x equals 0. We don't actually have what f is, so we can't get the y value, at least not without anti-diff, but even then we still don't really know how to get the plus c afterwards. But that's besides the point anyway. Point being is I want to know at x equals 0, is this a turning point or is it an inflection point? And if so, do we have max or min? So what do we do for finding nature of the stationary point? Double derive? Yep, easy. F dash dash of x means finding the derivative of this, so 8x. All right, we've double derived. What are we doing here? Sub x, yeah, sub in x equals 0, yes, because that was our x coordinate. That's the one that we want to test. So f dash dash of 0, 8 times 0 is 0. From here, what does it mean if our double derivative is 0? What type of point have we found?
It's an inflection point or a point of inflection.
Yeah, point of inflection. If you wanted to be super specific, you would say stationary point of inflection, but I'd be really shocked if someone pulled you up on that. That's just me being pedantic. And that should kind of make sense too, because if your derivative is a quadratic, it pretty much implies that the original function should have been a cubic, right? Like if I had f of x was, what exactly would it be? Nah, forget it. just for demonstration purposes, if we had x cubed, then the derivative of a cubic always goes down to a quadratic. We had a quadratic here, so if we think about what the stationary point of a cubic is, or at least this kind of cubic, it should have been an inflection point. So yeah, that's pretty much it there. Everything else in question 1 is just going to be some version of that, doing either, you'll either get a positive, a negative, or a 0. You're just reading off the criteria. Okay, what's that? Stationary points in nature, stationary points in nature. Yeah, there isn't a whole lot unique here. A lot of it kind of borrows from the previous chapter, which is you got to find the stationary point and then figure out its nature. Question 5 looks like it might be unique. Let's see. Got an ax squared plus b, stationary point at x equals 0, always. Oh wait, we've got to prove that actually. That is kind of the same as before. Given p of x has a second stationary point at negative 2, 6, find the values a and b in the nature. Yeah, okay. So again, the bulk of what's happening here is actually just finding the stationary points. I think this might be unique enough to do. Yeah, okay. So we have p of x is equal to x cubed plus ax squared, ax squared plus b. We have to prove a stationary point at, where is it? At x equals 0. So a little bit different now that we're trying to prove that a stationary point appears at x equals 0. Although the overall steps are going to be largely the same. So who can speed me through it?
We're going to find p dash of x.
Yep, that's it. P dash x, 3x squared plus 2ax. All right. What now?
Can we double derive?
Yeah, because you do want to. Well, I guess this one isn't about nature just yet. So if you wanted to find the nature at x equals 0, which you will eventually, then you double derive. For now, we're just trying to prove that it exists to begin with.
So can we just equate it to 0?
Yeah. We equate this to 0, not because this is 0, but because gradient should be 0. So basically, we want to prove that 3x squared plus 2ax equals 0 has a solution of x equals 0. So how are we going to reveal that solution based on, well, you can probably just see it, but if you subbed in x equals 0 into both of these spots, it would equal 0. How do you more clearly reveal that?
Can you create a null factor rule equation?
Exactly. You take common factor of x out the front, 3x plus 2a. That's going to give you two solutions, x equals 0, which is the one that we wanted, excuse me. And then we had 3x plus 2a equals 0, under which case x equals negative 2a on 3. Those would be the two stationary points of this. So, bit of a nicer version of the literal equations. This one didn't have a power of n in it. When it's just coefficients, it's not nearly as bad. Now, part B is an interesting part because we're told that the second stationary point is at negative 2, 6. So we have another stationary point, negative 2, 6, and we need to figure out the values of A and B. Well, and the nature, but I have realized we hit time there, so I'll just sort of talk about this broadly speaking. This second stationary point should only ever be able to refer to this. So if x is negative 2a on 3 and x is negative 2 here, then you equate negative 2 to this. That'll give you your a pretty quickly. Then once you have your a, it means you've only got one unknown left in this. You can sub in any coordinate that you know now, and we do know this coordinate, x equals negative 2, y equals 6, negative 2 in all of these x's, and then the y equals 6 here. That'll get you your b pretty quickly. That's about it for that one. So if there's anything further to quickly clarify, please be sure to stay behind for a bit, otherwise I'll let you enjoy the rest of your day.